I am Devlin. I've been at 8flight for 4 years. Yeah, so basically, I wouldn't consider myself in any way an expert on Web3. However, I did become somewhat obsessed with it when we ran an internal, someone ran an internal course for us at 8flight, quite a long form course on how to program in Ethereum. And I just found the whole technology, the whole totally kind of brand new paradigm for this technology really interesting. And I wanted to know how the inner workings of it, the fundamentals underlying the kind of virtual machine of it all actually worked. So I'm not going to look at the chat while I'm presenting, but if you want to ask any questions during it, I will look through it at the end, or you can ask them at the end and I'll try my best to answer them. So this talk is kind of about understanding the fundamentals of how blockchain technology works. This will be examining Bitcoin, which makes sense, as you probably are all aware, as the first cryptocurrency. And so I think once you have the understanding of how Bitcoin works, it becomes much more easy to understand how every other type of blockchain works. So let's go right ahead. So you're probably all aware that most of the internet is what we would call centralized at the moment, in that you type a website URL in your browser in your machine make a request over the internet routed using the IP address of that URL, and it arrives at a destination server somewhere, which is the thing that houses the website and sends you back a response over the internet as well. So by centralized, we mean there is one owner for the data or the website, and it's stored in one place. Obviously, in reality, it might be stored across several servers and load balanced and all sorts of fancy things, but really there is one owner and one place you go to retrieve that information, and one kind of entity is in complete control over it. So decentralized, on the other hand, therefore means there is no single point of ownership of the website or piece of or the data. So every node in the network has to contain the entire history of all the data of that network. So a client or a browser should be able to go to any single node and ask for data from them and get the same response from any node in that network. So the really difficult thing is for them all to come to agreement on what that data is and what the history of that data is. There have actually been types of decentralized networks for a long time. So you've probably all heard of peer-to-peer networks, but these do not work on a secure enough basis to be used for example, financial transactions or any kind of data that a company or entity would want to keep secure. Obviously, in peer-to-peer networks, the idea is that you either get the song or the video or the picture or whatever that you've asked from the network, and you know whether you do or don't get it in the end. So there's not much worry about, well, I mean, there's a lot of worry about security, but no one's using it for financial data, for example. There are also kind of partially decentralized networks, which are more secure, but at base, they always rely on some kind of centralized mechanism to agree on what the data actually is. So one example is a rotating leader mechanism or something like that, which you can probably understand what that means from the name of it. So this was Bitcoin's true innovation. It was creating a mechanism for all nodes to come to consensus about what the data is without needing a centralized mechanism to tell them what it is, and to do it in a completely secure way. So Bitcoin was created in 2008 by Satoshi Nakamoto, who to this day remains an anonymous person, group, entity, which is obviously extremely fitting for the very first cryptocurrency. So that's going to be the basis of this talk. How do you come to consensus across across a network of nodes without trust? So Bitcoin, we can imagine it to be basically like a simple accounting ledger system. If you've ever used the app Splitwise, it's like that. So let's say that Maureen, Nynaeve, and Lan, some of you might recognize those names, go on a magical quest. This ledger would record that on the quest, Maureen Nynaeve paid £100 for something for Moraine, and Lan paid £50 for something for Nynaeve. So once they finish the quests, according to the ledger, that means that Moraine, if you simplify the debts, just owes Nynaeve £50 and Lan £50. Except obviously it's not pounds, it's Bitcoin, a completely virtual currency or value. And the quest never ends. So people are just trading these values back and forth all day. And then obviously we've made a way for you to trade traditional currencies in and out of these exchanges for virtual Bitcoin. So for those who haven't, oh yeah, there's the Bitcoin sign. So for those that haven't seen this, there are third-party providers of Bitcoin, Ethereum, whatever cryptocurrency wallets. You just need to go to the website and create a wallet, or go to your phone and create a wallet in the app. So these are third-party providers who just have a node in the Bitcoin network or the Ethereum network or whatever. And if you have your wallet, like on the right-hand side, you've got an Ethereum wallet with MetaMask, you can send Ethereum to anyone else's wallet, as long as you just have the account number there at the top. And they can't stop you sending money to their wallet, but they probably wouldn't want to. So there you go. So the third-party provider who has the node in the network, once you've clicked to send the money, it broadcasts that you've made that transaction to all the other nodes in the network via the internet. So these third-party providers, and as soon as other nodes hear about a transaction, they broadcast it to all the nodes they're communicating with as well. So the transaction makes its way around the network, kind of instantaneously, very, very quickly. So, okay. The question is, how can a node be sure that it really was Alice sending her money to Bob and not someone pretending to be Alice's wallet? How does a node verify that a transaction is real? So it'll be unsurprising that a lot of cryptocurrency is based on cryptography basics. So you've probably heard of public-private key cryptography or asymmetrical cryptography. This is what SSH is. So whenever you make a remote pull or push request to GitHub, you're probably doing it via SSH, and which is this public-private key cryptography. So every wallet has a associated public key and private key. And by the way, a key is just a large computer-generated number. So when Alice uses her wallet and takes Bob's wallet's address and clicks to send him 1 Bitcoin, her wallet software cryptographically signs the transaction in the same way as we do in SSH. So signing basically means you take the transaction message of wallet at address X sends 1 Bitcoin to wallet at address Y. You take the private key, which is the encryption key, you put them through an algorithm to encrypt the message, and out pops this hello Bob kind of signature. And their signature is just another large number and encrypt the encrypted result of the algorithm. Then the broadcasting node sends that encryption, that signature, plus the Alice's wallet's public key, not her private key, obviously, and the transaction message, the original transaction message. The receiving node, you basically uses the reverse algorithm. So it takes the Alice's public key and it decrypts the signature. And if what pops out is exactly the original transaction message, then we can be sure that only the person holding the encryption private key could possibly have encrypted it correctly. So this is one of the ways in which cryptocurrency is extremely secure. It's literally impossible, just about, to pretend to be someone else's wallet unless you have their private key. And it's impossible to guess someone else's private key or calculate it or reverse engineer it. And we'll understand why it's impossible a bit later on. This is also, by the way, the reason why you've heard about people losing fortunes in cryptocurrency, because once they've lost access, once they've lost their private key, no one can get it back for you. And that wallet will be locked forever. Okay, so that's how you verify, that's how nodes hearing about transactions can independently verify that those transactions are legitimate. So now we have a system where each node in the network, when it joins into that network, downloads the entire history of transactions from the beginning of the network. And each node has a way of verifying every single transaction by itself. It's also useful to know that a wallet cannot borrow extra cryptocurrency and cannot overspend. So if every wallet can only spend the money that it actually has in the wallet, and if you have the history of all transactions that have ever taken place, then another thing every node can do is verify that the wallet does indeed have the actual money to transfer. So let's consider double spending, which will help us understand this even more. So Matt sends 1 Bitcoin from his wallet to Lan for a new horse. He tries to send the same 1 Bitcoin at exactly the same moment, or 1 second later, to Nynaeve for an enchanted knife. Let's say he manages somehow to broadcast these 2 different transactions to 2 different nodes simultaneously. So what happens as those transactions reverberate around the network and nodes now have to decide which one is legitimate? So here we go. This is what blocks really are. A Bitcoin block is literally just a list in order of 1,500 to 3,000 transactions with some metadata. And then each block is inserted into the chain sequentially. And now you have your ordering of transactions. So you know that Matt paid for the horse first, and therefore the second transaction to Nynaeve is invalid because his wallet no longer contains that money. So blocks are how you come to agreement about the ordering of transactions. So the question is, so this question, by the way, as an interesting aside of how nodes trustlessly come to consensus about their data and how to order their transactions and so on, was actually first described in game theory in a paper dating all the way from the 1980s, and it's called the Byzantine generals problem. The idea goes that separate allied armies surround Byzantium. If the majority attack at exactly the same time, they'll invade successfully on the left. And if they act in some kind of different way to each other at different times, they'll lose. They need to find a way to agree to act in the same way at the same time. The problem is that messages that they receive may be sent by Byzantium defenders as deceptions, or even another general who's acting maliciously for some reason. Many solutions have been attempted over the years about how to overcome the Byzantine general problems of coming to consensus trustlessly. Bitcoin's biggest innovation was that it was the first that achieved this successfully in code. So how does it do this? How did Satoshi make this happen? You've probably maybe heard of the Proofofwork consensus algorithm, which is what Bitcoin uses. And this all boils down to winning a computational lottery. So let's do another quick cryptography revision. Hashing. Hashing functions like MD5, SHA-2, or CRC32 takes any input on the left, puts it through the hashing function or algorithm, and produces a string output, which we call the hash or the digest. So these hashing functions and the hashes or digests have some very special qualities. The hash produced is always a fixed length. Let's say in this one, it's 256 bits. It will always be, the same input will always produce exactly the same output hash, but if even one single character of the input changes, the hash produced as an output completely changes. So you can see that the 4 on the left at the bottom, for example, produce completely different digests, even though they only have minor character changes. To this day, even though these hashing algorithms are public, no one has ever been able to reverse engineer a way to get the input from the output. And it would be a very difficult situation if that did come to pass. It's one of the worries about quantum computing, whether that will be possible, because this is the basis of a lot of cryptography and cryptocurrency. So the only way to find what input produced a given output is literally running through inputs until you find the correct output hash that you're looking for. So this is what all nodes are doing, all mining nodes are doing all the time in the Bitcoin network. They're continuously running through endless inputs, putting them through a hash algorithm until they find the one that produces the output hash that they're looking for. But what are they trying to match? So we know that each output hash has 256 bits. Statistically, that means you would have to make 2 to the power of 256 input guesses in order to find the one you're looking for. This is such an impossibly incomprehensibly large number that it would take billions and billions and billions and billions of years of all the computing processing power on Earth to guess a single one. So that's the reason why it's impossible to guess the encryption private key of someone's crypto wallet. It's more or less, we can say, literally impossible. So instead of that, Bitcoin says you don't need to find an output hash of 256 bits. You only need to find an output hash where any output hash where the first 15 digits are zeros. So now it only takes, on average, say 1,000,000 billion guesses before finding any output hash with 15 zeros at the beginning. This is what is called the target difficulty. And they're not just using any input to find any output which has 15 zeros at the beginning. Each mining node takes the previous block's output, hash output, the current timestamp, a special combination of all the transactions to be included called the Merkle root of all the transactions. And then they use a nonce number, i.e. a number used once, i.e. any random number that they keep changing so that they keep getting different output hashes until they find one that starts with 15 zeros or that meets the target difficulty. So yeah, so that's how each block is constituted, and that TX or transaction root is the Merkle root, which is a list of all 3,000 transactions hashed down to single hash and then hashed all together again and to generate the hash of the block. So here is a block I made earlier. No, I'm kidding, I didn't make it. But you can go to blockchain.com or any number of websites to see all the real blocks in Bitcoin, Ethereum, wherever you want. So we can see the hash of this block. It starts with 19 zeros at the beginning. I think that's the current, maybe perhaps the current target difficulty it was at this time of what Bitcoin actually is. The following characters, by the way, are numbers and letters because it's in hexadecimal format rather than binary format. If we move on, and you can also see the difficulty, the Merkle root, the miner is unknown, timestamp, etc. This is a list of all the blocks. Whenever I took this picture, you can see that they're trying to go for an average of one every 10 minutes in Bitcoin. I'll explain that more later. Okay. So, yay, you have won the computational lottery. you've hashed together all of those things you needed to hash. You've kept changing the nonce until you found the target difficulty. You found a output hash which meets the target difficulty. Your node broadcasts its winning block to the entire network. Every other node immediately validates this block, that every transaction is valid according to the verification process I outlined earlier, and that it can also generate the same output hash using the same metadata that you did. So what happens now? Are all the other miners able to store up blocks they've also found that meet the target difficulty and then release them after yours? They can't, unfortunately, or fortunately, I guess. Firstly, because it's likely they'll have transactions that are already included in your new block. That would change the Merkle root if they had to change transactions. They also need the block, the hash of the new block and swap that out for the previous block. the timestamp will also have changed. And all of these individually mean that all of their previous hash calculations are now useless, because remember, like any different input will generate a totally different output now. So more or less what this boils down to is that every single miner has to completely restart their mining process with every single new block. And this is by design. This is what the proof of work mechanism really is. A quick aside, if you win the block, you win Bitcoin as a reward. So one of the transactions included in your block will be a transaction awarding you Bitcoin. And this is the only way that Bitcoin is minted, new Bitcoin is minted. So the proof of work mechanism, let's explain it more. If we assume that a majority of miners in the network are acting honestly because they're incentivized to win Bitcoin as a reward, and by the way, that's not a big assumption. It's very normal to assume that the majority of miners are acting honestly. That's because if it was known that a network had a majority of bad actors, then the virtual currency would, the markets would immediately lose all faith in that network, and therefore it would completely lose all value and no one would be part of the network anymore. And there's another reason as well why most miners are acting honestly. And that is because you cannot fake doing this computational lottery. So all the other miners will be immediately able to check whether you really did find the correct nonce or whether all of your transactions are verified and whether you've actually generated the correct output, which means that even if you're trying to hack the system, you still need to do the entire intensive computational lottery. So having to spend all that money on machines and electricity incentivizes most miners to act honestly. You're more likely to make money simply by following the system than trying to hack it. And this is ultimately why the proof of work mechanism works. So now we know how blocks are mined and what it is mining computers are doing all day. Let's see what's next. Yeah, so there is a couple of other things to know about. If you have two blocks and they're both mined at the same time-ish on different ends of the network, let's say, then all nodes who hear about two different chains will always drop the smaller chain, which becomes useless, and they'll immediately start working off whatever the longer chain is. If two chains are the same length, then there is a couple of other factors they use to decide between them, such as who had the earlier timestamp, for example. So what happens if you were the miner on this B2 branch and your chain is suddenly dropped from existence? This is actually something that's really interesting about blockchains. The only reality that exists is the valid chain. So the Bitcoin reward that you have in your wallet from your B2 block that you mined will simply disappear from your wallet as if by magic. And the same thing happens to all the transactions that you included within your block. For all those people, all the money will reverse history as if it never happened. You see the Bitcoin disappear or reappear in your wallet. In reality, you don't actually see Bitcoin reappearing and disappearing. And it's for this very reason that chains can be superseded. So instead of immediately showing that the Bitcoin has transferred, vendors will wait for several blocks called confirmations in this context before they actually deem a transaction to have taken place, because it could be replaced by a different chain, in which case it won't have taken place in reality. So for small transactions, this is something like around 6 confirmations or blocks. And for big transactions, it might be dozens. So another interesting thing is that Bitcoin can algorithmically control how often the hashing puzzle is solved. And it is set to keep this to roughly statistically once every 10 minutes. And it can do this by increasing the target difficulty, increasing the number of zeros at the beginning of the output hash that you need to find. And it does this every 2016 blocks based on the time it the average time it took to find to mine the previous 2016 blocks. This apparently was just something Satoshi chose in terms of why it's 10 minutes. He, from what I've read, thought this was a good trade-off to cancel out the bonus mining time that the winning miner gets from being the first to start mining on a new block. But many people argue that this should have been far, far lower than 10 minutes. And Bitcoin is considered to be, I think, by far the slowest network, like extremely slow compared to more modern blockchains due to this 10-minute rule and the fact there's only roughly 2,000 transactions in each block. Also, there is the Bitcoin that you're allowed to reward yourself for winning the block is fixed, and it is halved, also algorithmically, every 210,000 blocks, which equates to roughly every 4 years so far. That's because Bitcoin is programmed to cap out to stop completely minting at 21 million Bitcoins, which is estimated to happen in 2140. Satoshi chose to do this so that Bitcoin is deflationary rather than inflationary, so that they keep increasing in value, even though new ones are being minted. But different cryptocurrencies do this differently. Some are unlimited and therefore inflationary. So the reason why now it's still valuable to be a miner is because of the transaction fees. So whenever you transfer a Bitcoin from your wallet to someone else's, now you have to pay transaction fees, and those fees keep increasing. It's now very expensive to do a transaction in Bitcoin or Ethereum, the oldest blockchains. And the winning miner keeps all of the fees from all the transactions as well. So the idea is that once the reward is low enough or disappears altogether and no new Bitcoin is being minted, that hopefully the fees would be high enough to keep the network going, but we don't know what will happen. So to tie it all together, let's take a look at what is called a 51% attack. This is one of the only ways that cryptocurrency is susceptible to attack. So if you think about it, the proof of work mechanism means that your likelihood statistically of winning the next block is directly proportional to your relative amount of processing power in the entire Bitcoin network. Because winning the hashing puzzle each time is a statistical likelihood. So if you own 10% of all processing power in the Bitcoin network, you will win on average 10% of all blocks. So originally miners competed as individuals with individual machines. Now the difficulty target is far too high for that, so they have to join together into mining pools. So as you might guess, a 51% attack can happen when a single mining pool controls 51% of the total processing power of the network. So let's go back to the double spend scenario. Matt sends 1 Bitcoin to LAN first for a horse. He waits for LAN waits for 6 confirmations, thinks everything's fine. No way that a new network is going to supersede that now, and sends the horse to Matt in real life, and Matt receives it in real life. However, what LAN didn't know is that Matt controls 51% of the Bitcoin network. So while the rest of the network was working on that chain, making the 6 confirmations, Matt was nefariously building his own chain behind the scenes privately, and he can do this statistically faster than the rest of the network. So once he receives his horse, he suddenly drops a chain of 7 confirmations onto the network, which supersedes the other chain, and all miner nodes automatically drop that one and begin working on his instead. However, Matt did not include his transaction to LAN inside those 7 new blocks. So suddenly the Bitcoin really does disappear from LAN's wallet and reappears in his. History is effectively reversed, except that Matt still has the horse and nobody knows who owns the wallet. So the police can't track him down. And that's one of the only ways in which you can reverse history and do a real double spend. So these days, mining pools never attempt to go above 40% of the total mining power, else this would immediately attract suspicion and may ultimately have the effect of killing the currency, as no one would trust it. However, 51% attacks have happened as recently as last year. From what I could tell in my research, I don't think it's ever happened to the OG Bitcoin, but it has happened to newer forks of Bitcoin. And by the way, forks is a whole other fascinating thing that cryptocurrencies can do, which we definitely don't have time to get into right now. So now you can really understand why it's called mining for Bitcoin and why it's called the proof of work consensus algorithm, because dang, it sure do take work. And it's probably also clear now why Bitcoin is terrible for the environment. If you imagine thousands of miner machines endlessly processing endless numbers, all for the same block, and all restarting the process all over again with every single new block that comes in. So thankfully, there have been many advances to blockchain technologies since Bitcoin, the very first. And there are new types of consensus mechanisms which aren't proof of work. For example, you may have heard of proof of stake, which Ethereum is converting over into using now. Or, for example, a really modern one is Solana's proof of history consensus algorithm. So to conclude, blocks are, you can think of blocks as just lists of transactions. Each mining node aims to win the computational lottery each time by finding an output hash that meets the target difficulty from the list of all of its transactions hashed together. The proof of work algorithm incentivizes honesty or acting faithfully. So all nodes can come to agreement about ordering transactions, and this is done so securely that it is used in finances as a currency. And this is how you add a block to the Bitcoin blockchain.